Hello, today is our second day on 9-2 graphing simple rational expressions, and we're going to focus on our real world application today. So our first question, you and your friends are sponsoring a dinner. The cost of catering the dinner is $9.95 per person, plus there's an $18 delivery charge. We want to write a model that gives the average cost per person. So we think about it. If one person is going, they have to pay $9.95 for themselves, plus they're the only ones responsible for that $18 delivery charge. If we have two people, we've got $9.95 per person, but then those two people split the $18 delivery charge. And if we have three people, we've got $9.95 people for the plates, and then those three people are splitting that $18 delivery charge. So we know that the total cost is going to be $9.95 per person plus the $18 delivery charge. But that's the total cost, that's not the average cost. To find the average cost, we have to divide by how many people they're going to be. That's what's going to divide that $18 per person. So I used C and P as my variables. You could use X and Y, you could use A and B. Then P is representing the number of people, and C is representing the average cost. Some people prefer to use variables that are representing the actual thing. Others prefer just to use X and Y. Just remember that X is representing the independent variable and Y is representing the dependent variable. So when we look at our axes on our graph, P is the X and C is the Y. Sketch the graph of the model and use to estimate the number of people needed to lower the cost to $11 per person. So if you don't have your calculator out, go ahead and get it out. We enter our equation in. Don't forget that when you enter the equation in, we have to put those parentheses around the numerator. So we've got 9.95 x plus 18, close that parenthesis, divided by x. We always start off with the standard window, zoom 6. And we see this graph right here. We know that we have a hyperbola, so we know that we need to have two sections of it. So I need to find that other section. If the average cost is up at 18, I'm going to change my window. I'm going to make the x max, let's just go 25, and the y max 25. So remember, sometimes it's just kind of a guess and check. Alright, so now that we can see both pieces, let's go ahead and sketch our graph. We're going to focus our attention to this part over here. This is what's going to be representing the real world application. Since our X is the number of people, we can't have a negative number of people attending. So we're going to start with the quadrant 1. That's representing what's possible, what's realistic in the real world. So we want to sketch the graph, which we did, of the model and use it to estimate the number of people needed to lower the cost to $11. If I am lowering the cost to $11, we want our Y value to be $11. So there's a couple different ways we can do this. We can try tracing. So we trace and we keep on going until we find our Y to be 11. Oh, our cost is going up. We're going the wrong direction. Keep going, keep going. We're getting closer, getting closer. Alright, so we know it's going to be between around 17. Another better way to do this is go to y equals. If we want our cost to be 11, we type 11 into y2, because remember that's going to give us a horizontal line at 11. We graph. We go to second trace. We want to find the intersection. First curve, enter. Second curve, enter. Guess. And we've got that horizontal line right there. That intersection point is at 17.14, comma 11. What that's telling us is it's going to take about 17.14 people. Now we know we can't have, a fraction of a person. So what we're going to do is we're going to say just about 17 people. Now if it said it had to be at least $11 or at most $11, then you would have to make sure that you're rounding in the right direction. But here we're just going to round down to 17 people. There is another way you could have done this as well. We could have done it algebraically. If our y or our c value is 11, we plug that in for c. 9.95p plus 18 all over p. If we want to solve this, we make that into a fraction. We cross multiply to get 11p is equal to 9.95p plus 18. Move that 995 over to the left by subtracting. We're left with 1.05p is equal to 18. Divide by 1.05 and we get p is about 17.14, which is exactly what we found when we traced and exactly what we found when we found our intersection point. So a bunch of different ways that you can go about solving that. Part C, describe what happens to the average cost per person as the number increases. So we're saying when we have one person, we know they're paying that whole $18 charge by themselves. As we have more people, the average cost per person is going down, 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 down. But it's going to approach the value of $9.95. It's never going to get below $9.95. It's never going to get to zero because every person has to pay that $9.95 for their plate for dinner. What we're splitting up is that $18 service charge. If I have 1,000 people, they're not even paying a penny a piece for that $18 service charge, but they're still having to pay that $9.95 for their meal. So the more people, the average price goes down. But the most important part is noticing that it approaches $9.95 per person, but never reaches. That's that asymptote. Alright, so there's our first problem. We've got one more left and we're done. Alright, this one is a geometry application. So I'm sure you remember all the way back last year to geometry. The formula for the sum of the interior angles of a regular polygon is 180 times n minus 2, where n is the number of sides of a regular polygon. So this formula tells us all the angles, what they add up to be inside. Write a model that gives the measure of each interior angle. Well, if we're going to have A for angle, if 180 times n minus 2 gives us the sum of all of them, and we have a regular polygon, meaning that every angle is exactly the same, we take the total number of degrees of all the angles and divide by how many sides we have. That's how many angles we have. So again, A is going to be the measure of each interior angle, and n is the number of sides. We want to sketch a graph of the model and use it to estimate an interior angle of a regular 40gon. So we go, and we know that in this case A would be y, n would be x. So we clear out what we had before, making sure again that our numerator is in parentheses If we don't have that whole thing in parentheses, we will have a mistake. Our graph will not be correct. Divided by x. And we start back with our standard window, zoom 6. And we know that's not going to help us very much. We have an interior angle measure of 180. We are looking for a regular 40-gon. Now you could go ahead and play with your bounds with the window, but I think the easiest thing to do is go to zoom, arrowed all the way down until you get to, oh, I went too far, so you get to zoom fit. And that will bring you to your graph. So we're going to go ahead and sketch that. And again, if you want to look at the window, you can see that we have x's, our y's are in the thousands, our x's are from 10 to 10. We want to change that x because we know that we are looking for an interior angle measure of 40-gon. We know that we're going to have to change that up a bit. So if we're looking for 40, I'm going to change that to 50. Doesn't look too much different. We want to estimate the interior angle measure. One option is to trace. And I'm not too fond of that option because it's not very accurate. Or, since 40 is representing our x value, we don't have to do the whole intersection thing. All we have to do is go to second trace. Number 1 is finding the value. We want to find the value when x is equal to 40. And we see that when x is equal to 40, our y value is 171. What that's going to tell us is a 40-gon has each interior measure of 171 degrees. Now, just like before, there is another way we can do this as well. We can do it algebraically without our graph. We have our angle measure, each angle which we're trying to solve, 180 times n. We've got 40 sides minus 2 all over 40. That gives us 180 times 38 all divided by 40. And once again, we get that 171 degrees. And then our last question, part C, describe what happens to the measure of an interior angle of a regular polygon as the number of sides increases. Remember, our number of sides is representing our x. So as our x gets bigger and bigger and bigger, and we can go ahead and trace this, as x gets bigger, we see that our y is getting bigger and bigger and bigger and bigger as well. It's approaching an asymptote of 180. So that graph is going to forever go up, 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 approaching 180 but never reaching 180. So think to yourself, why can it never actually be 180 degrees? If it gets to 180 degrees, it's going to be a straight line. If it's a straight line, it's no longer a polygon because it's not going to be an enclosed figure, it's just going to be a straight line. Once it goes above 180 degrees, it's now essentially less than 180 degrees again. So if I have, let's say, an angle, let's draw a straight line, if it's 90 degrees, and then I make it 100 degrees, and then I keep on going more, 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 as soon as I get to 180, it's a straight line. As soon as I pass that 180, that would be my angle measure, which is less than 180. So what describes what happens here? It increases, approaching 180 degrees, but never reaching. It can't reach 180 degrees because it's a straight line. Alright, so it is very important that as you are looking at the application questions that you are able to describe what's happening. What are your variables representing in the real world? You will find this on assessments, so make sure that you are prepared for those questions.